So when I saw you guys last time and we did multiplication and division of fractions aren't that bad. They tend to be the easier thing to deal with because if I'm multiplying, right, a fraction, we can just multiply straight across, right? If I had 2/3 times 1/5, I would go 2 times 1 is 2, and 3 times 5 is 15. And that'd be all there is to it. And even when there's variables and stuff like that involved, it's still going to work the same way, right? We may have to reduce that fraction when we get to the end, just like we would if it was numbers that needed to be reduced, right? But it's still just multiplied across. And when we had division, if I had 2/3 divided by 1/5, we would just turn it into a multiplication problem by multiplying by the reciprocal. Anything that comes after the divided by, we would write as multiplication and we would just flip that fraction over, right? And then we would wind up with 10/3, right? And that's what we did the last time, only we were doing it with polynomials, right? But when we add or subtract fractions, what do we need? It's $1 million question, like a million imaginary dollars, because I don't have $1 million. But what do we need when we are adding and subtracting fractions? It is the thing most of you hate the most about fractions. So much so that you've mentally blocked it and can't seem to answer the question. If I am adding 2/3 to 1/5, what do I need? This is a common problem that people don't know the answer to this problem. You have to have the same denominator. You have to have what we call a common denominator, right? Does that ring a bell? Or has it been so long since you've... So in this circumstance, I don't have common denominators. This one's a 3 and this one's a 5, and they have to be the same. So if I multiply this side by 5/5, and I can do that because it's the same as multiplying by 1, and I multiply this side by 3/3, I would have 10/15 plus 3/15. And then I can go ahead and add them together, right? And I would go 10 plus 3 is 13, and I would have 13/15, right? And the same would be true with subtraction, right? I have to have a common denominator. Well, with what we're starting with, we're going to start out dealing with polynomials that have like bases already, common denominators, like bases. You might hear them pronounced, used interchangeably. So, let's write down some steps here for dealing with our problems. So, when we are adding or subtracting, we want to, 1, rewrite using a common denominator. Number 2. Combine the numerators and keep the denominators. Wow. Sound like someone was just thrown up against a wall next door. And last, we would simplify whatever we have left, if necessary. Remaining expression, right? Because we want to write it in its simplest form. So those are our rules for adding and subtracting. Everything else we're going to do is just examples. We're going to do examples on examples of every kind of adding and subtracting I can figure out. And we are going to start with a blue pen. Because I like blue pens. We're going to start dealing with like bases, and then we're going to move into different ones, right? So we're going to start with things that have a common denominator, and we are going to work our way into things without a common denominator. So our first example will be 13a over 4a squared plus 5a over 4a squared. Now, when I look at this problem, they have the same base, right? They're both over a 4a squared. So we can just combine our numerators. We have 13a plus 5a. Well, that's going to be 18a over 4a squared. So we've done the combining the numerators and keeping the denominators. The last thing we have to do is simplify the remaining expression. And we know this can be simplified because there's 2 even numbers, right? There's an even number in the numerator and an even number in the denominator. So we know those could be divided by at least 2. And we know that there is an a in the numerator and 2 a's in the denominator, which means that we can pull an a out of each of those as well. So if I divide 18 by 2, I'm going to be left with 9. If I divide 4 by 2, I'm going to be left with 2. Here, I have 1a, and here I have 2a's. And if you remember the last time I saw you, we're going to go, the one with the higher number of a's is going to get all of the a's, right? So in this case, our a squared is bigger than our a. So we know all of the a's are going to wind up on the bottom, right? And I'm going to go, well, there's 2 here and 1 here. So 2 minus 1 is just 1, which means that that bottom is only going to have 1. There's not going to be an exponent on it. And this would be our final result, completely simplified. Does that make a little sense? Did you follow with that? I really hope so, because they're going to get harder. Excellent. What if, let's go up here. Let's use some of this space so I don't have to move all of the directions now. What if I have 9x plus 12 over 16 minus 7x plus 12 over 16? Now this one I wanted to talk to you about. It's really similar to what we just did, except for because it's minus. If you remember when we subtracted polynomials before, we would have to distribute that minus to each piece. I want you to keep that in mind when you're doing this. Think of this as having parentheses around it. And we would rewrite this as 9x plus 12 over 16 minus, right, minus 7x minus 12. It's supposed to be 2, but I wrote the problem wrong, but we could do it that way. Does that make sense? This minus has to distribute to this part and to this part. We have to remember that it needs to change the sign of everything that follows it, right? Once we get it all together down here, we don't have to deal with that anymore. We can go start combining our like terms. We'd have 9x minus 7x. Well, that's 2x. Now we have 12 minus 12, which is just 0. So this becomes 2x over 16. And we can just simplify that because each piece is divisible by 2, and we'd get x over 8. So keep that in mind that we went over this when we were adding and subtracting polynomials as well, that negative's got to distribute to each piece. So even though it's not in parentheses, we have to remember that that's going to change the sign of everything that comes after it. Next example is going to be getting a little bit more complex, right? Because these have been fairly simple so far. And now we want to talk about what happens when we have to break things down a little bit more, like y squared plus 8y over y squared minus 9 plus y squared, 2y, sorry, plus 21 over y squared minus 9. So these have similar denominators, right? They're not even similar. They're exactly the same. So I can go ahead and combine the numerators. I go, well, y squared, well, there's nothing I can add that to, so it's just going to be y squared. And I have 8y plus 2y. Well, that's plus 10y. And I don't have a constant here, but I have this plus 21 here that I'm going to have to bring over. And then here, it's all going to be over y squared minus 9. And now we have to talk about the simplifying. And this is what we did last week. We got to these points and we did simplification. And so, which means we have to factor everything, right? I know I can look at this and go, well, my factors of 21 that add to 10 are 7 and 3. So I know that this can be y plus 3, y plus 7. So I'm going to write those right here. Y plus 3 times y plus 7. This down here, I recognize as a difference of squares. Anytime I have a perfect square minus another perfect square, we can always multiply them by their square roots, right? Y plus 3, y minus 3, right? Because the square root of y squared is y, and the square root of 9 is 3. We know that we can write them this way, right? As one of those special products that we dealt with before. What it does is it allows us to reduce these fractions. Anything that's the same, we can reduce. So I have a y plus 3 over a y plus 3, so those just cancel. And we are left with y plus 7 over y minus 3. So that one was fairly more complex, right? Can they get more complicated than that? Absolutely. Like you might have to reduce more things down. I would say always find that common denominator as best you can first. If you have a complicated denominator, you're going to want to try and reduce it just to see what they have in common so you know what to multiply and go, what do I have in this one that I don't have in that one? So let's do some that don't have similar or the same denominators. Let's work on some of those kind of problems. So if I have, let's get warm in here. So here I have 15 over 2x minus 16 over 3x. Clearly not the same denominators, correct? Can I help you with something?
This is timeless so that you control the summer class thing. I just want to talk to you about that, but if you're busy.
I have classes this period and next period. Are you high school?
Yeah.
Okay.
But I can come back a later time.
I have a free period at 2:05. If you're, you'll be gone by then.
Yeah. I can come back Monday.
Yeah, if you come back Monday, like second or third period, come in one of those periods and just, it'll only take a few minutes, but sorry about that. And sorry about that to you guys too. So clearly we don't have common denominators here, right? 2x and 3x aren't the same. They both have x components in them though, so we don't really have to worry about that. They're both multiplied times x. So I can go ahead and multiply this one. This one's got a 3 that this one doesn't have. So I'm going to multiply by 3 over 3 on this side. This side has a 2 that this one doesn't have. So this side I'm going to multiply times 2 over 2. And we can do that because multiplying by 3 over 3 is really the same as multiplying times 1. We're not changing the value of it. We're just changing the way it's represented. So 15 times 3 is 45. 2 times 3 is 6, so this is going to be over 6x. Minus 16 times 2, that's 32, over 3x times 2, which is also 6x. So we have our common denominators now, and we can just go ahead and do the subtraction. 45 minus 32 is 13, and 6x minus 6, well, denominators just stay the same, right? I can't reduce this fraction at all. And the reason I can't is that 13 is a prime number. Nothing smaller than it is going to divide into it. So this would be our final answer, right? It cannot be simplified beyond that. Will they all be that simple? Heck no. What would you need me for if they're all that easy, right? And you're like, that wasn't that easy, Miss Hoy. What if I have 4a over a squared minus 7 over 8a? When I look at this, it's going to be similar. I'm going to go, okay, definitely don't have the same denominator, right? So I'm going to look at this a squared and I'm going to go, well, what does this one have that this one doesn't? This one's got 2 a's in it. That one only has 1. So this one's already ahead in terms of a, right? But this one doesn't have an 8 and this one does. So I'm going to go ahead and multiply it times 8 over 8. This one, I'm going to go, well, what does this one have that this one doesn't? Well, it just has one more a, right? They both have an a. This one has 2 and this one only has 1. So we're going to multiply this times a over a. 8 times 4a is 32a. 8 times a squared is just 8a squared. Minus 7 times a, well, that's just 7a. And then we've got 8a times a, which is just 8a squared. So now we have common denominators, and all we have to do is our subtraction, right? So we're going to go 32 minus 7. Well, that's 25. So we're going to have 25a over 8a squared. And then again, we're going to see what we can do to reduce it. Now, 25 over 8 does not reduce because the factors of 25 are just 1, 25, and 5. And the factors of 8 are 2, 4, and 8, and none of those are common factors. And so those are just going to stay the same. But I have an A on top and an A on the bottom. And so here I'm going to be left with 25 over 8. 8. A 2 minus 1 is just 1, so it's just going to be 1a. Did that follow? Did that track for you? All right. Now they're going to get harder, which means I have to turn the page. Anytime you turn the page, you know stuff's going to get harder. Let's go back to green. I was kind of liking the green pen. Let's see. Let's start with something a little easier, and then we'll move on to more difficult. K squared plus 16 over 5k minus 10 plus. No, it's not plus. It's minus. Dang. I guess we could have done it either way. Minus 4 over k minus 2. Now, currently, these do not have the same denominator, but this one here is pretty factorable, right? 5k minus 10 has a 5 I can pull out of both pieces. So I'm going to rewrite this problem as k squared plus 16. I'm going to factor that 5 out. I'm going to call this 5. 5k divided by 5 is just k. Minus 10 divided by 5 is minus 2. And we can see where these are two pretty similar problems now, right? Because now when I look at this 4 over k minus 2, I can see that the only thing that it doesn't have that this one has is that 5 that's multiplied to it. And so I'm going to go ahead and multiply this times 5 over 5. And remember that 5 gets distributed to both pieces in here. And so we would be left with k squared plus 16 over 5k minus 2 minus 20 over 5 times k minus 2. Now, I could distribute that through, but I don't want to because I want to see if there's anything that I can reduce in the end, and it's so much easier to reduce things when they're in their factored form. Now that we have the same denominator, we can just do our subtraction. We've got k squared, but we don't have anything squared to subtract it from over here, so it's just going to stay k squared. I have plus 16 minus 20. Well, that's just minus 4, which is going to give me 5 over 5 times k minus 2. Now, if you look at this right off the bat, you think, oh, there's nothing that can be factored. But I know that k squared minus 4 is a difference of squared, right? K squared is a perfect square minus 4, which is also a perfect square, which means that we can write this as k minus 2 times k plus 2 over 5 times k minus 2. So we have this common factor in both of them, right? In the numerator and the denominator that we can cancel out. You have this k minus 2 over k minus 2. So our solution would be whatever is left over, k plus 2 over 5. Will they become more complex than that? Possibly. Likely. We have a little time. I'm going to do one that's a little harder just because I want to make sure you have ample examples of what to expect when you're doing your homework. But we'll just do one more. I have time to do one more. If I have x squared minus 5 over x squared plus 5x plus 6 plus 1 over x plus 2. Very different problems, right? So what I want to do is I want to factor first, right? I want to factor everything I can factor. So I'm going to rewrite this problem starting with this x squared minus 5. Not much I could do with that. That's going to stay x squared minus 5. X squared is a perfect square, but 5 is not, so we can't write it as a difference of squares. But this trinomial is factorable. And we can redo a lesson on factoring, but this would be x plus 3 times x plus 2. And then here we've got plus 1 over x plus 2. And so we're fairly close in terms of having a common denominator, right? If we look at this, the only thing that's different is that this one's also got an x plus 3. So I don't need to do anything to this side. I can just multiply this side times x plus 3 over x plus 3. And I don't need to multiply them through and figure all that out. They're better for us in factored form anyways. So now I can rewrite this problem, right? I have x squared minus 5 plus x plus 3 all over do it like that, all over x plus 3 times x plus 2, right? Well, these are being added, so I can combine any like terms, and I'd wind up with x squared. I don't have another x, so it would be plus x. Minus 5 plus 3 is minus 2 over x plus 3, x plus 2. So our last bit would be to break this down into factors if we can. Factors of 2 that are going to give us, that'd be x plus 2 times x minus 1 over x plus 3, x plus 2. So we just factored it out. And then all we have to do is simplify. So we're going to reduce and reduce, and we would be left with x minus 1 over x plus 3. And that would be our final answer. That will be about as complicated as a problem as you're going to get. Remember, this is all going to be done in Delta Math. Does anybody have any questions? Does anybody have a lot of questions and they're like, we just need to try this to know what questions to ask? Or you guys feel pretty good about it? Well, here's what's going to happen. Hold on, let me stop the video because there's really no reason to